Okay, so today we're just going to be talking about one sample z-ins, z-intervals. So we're just going to start with a little example, red versus blue M&Ms. So what we're trying to find is P, which is the proportion of blue M&Ms in the population. So how are we going to kind of start to find this? Well, we're going to do what we usually do in statistics, which is take a little sample, take a little piece of the whole population. Say our sample is 100, and we'll say that p hat, which is the proportion of blue M&Ms that we got in our sample, is 0.36. So a good place to start with this is to look at the sampling distribution of p hats for n equals 100, because this is always going to be different for each sample size. And so what we want to do is make sure that this is normal, this curve. So how can we do this? Well, we can check a condition. We actually want to check a couple of them. So first, we're going to call the normal condition to make sure this curve is normal, as the name suggests. So we want to say that p hat times n is greater than or equal to 10, and 1 minus p hat times n is greater than or equal to 10. And so this is essentially saying that the successes and the failures is greater than or equal to 10. And we want to do this because if we don't have enough successes or failures, then it's going to just kind of skew our interval in the way that we don't want it to. And so that'll just mess with our data in a way that we don't want it to. So we just want to always make sure that these are true. Next, we're going to check the random condition, which is just that our sample was randomly collected. This is pretty simple. We just want to avoid any extra convolutions that we don't want in our sample, and just kind of make sure that our data is clean, per se. Then the last condition is the 10% condition, which means that n is less than or equal to 10% of big N. Big N is the population. So for this example, we can just say that we had a ton of M&Ms, so much that 100 is just like not, as represented, this is not at all 10%. This is a lot less. So this is fulfilled for this specific problem, as well as the normal condition, which is because if we had 100 times 0.36 is 36, greater than or equal to 10. Same with 1 minus 0.36 is 0.64 times 100, also greater than or equal to 10. We're fine. We can say that the random condition is also met for this problem. But we want to fulfill the 10% condition because we want to make sure that each trial is independent. And we want to do this because if we have too big of a sample, we will kind of be saying that we're not sampling with replacement, which, because 10% isn't that much, so it's still going to be relatively accurate even if we're not replacing our M&Ms, but there could be just due to sampling variability, if you get too large of a sample, one that's generally greater than 10% of the population, it could really mess with your data, and we don't want that. So we just always want to fill that. All right, now we can start talking about the sampling distribution. So the mean is always going to be P, and P is an unbiased estimator of the sampling distribution. Then I'm just going to draw this standard deviations. Okay, so this is one standard deviation of P hat. What is the formula for this? This is the square root of P times 1 minus P over N. We want N because this is for N equals 100. The rest is just pretty basic, standard deviation. Okay, now I'm going to pose kind of a rhetorical question. What is the probability that P hat is within 2 standard deviations of P? Well, because we know that this curve is approximately normal as sampling distribution, we can say the 2 standard deviations. We just find the z-score is about 2. So it's right around 95%. So we can kind of reconstruct this into a new statement that says we are 95% confident. This is the confidence level. You want to star this. That P is within 2 standard deviations of P hat. And we can kind of just switch these two, and we really want to. We want to switch these two terms, P and P hat, because we don't know P, and so we're gonna try and infer where P is based on what we know. And we can just kind of make this difference because, if this is the 95%, the P, which is anywhere around this curve, is still equidistant, 2 standard deviations away. But we're inferring from this point instead of this point. So we're saying that if it's outside, then, there's going to be a 95% chance that this covers this, which is what we want. So we kind of have this we're solving for this unknown now. But we still can't fully do this because we don't know what the standard deviation of P hat is, because we're working with P and we still don't know what P is. So what we're going to do is we're just kind of substitute standard deviation of P hat for standard error, which is a new statistic. We're just going to substitute essentially P for what we know, which is P hat. So it's going to be P hat times 1 minus P hat over N. Again, we want to do this for N equals 100. Then we just kind of plug this in. So we have our sample proportion is 0.36 times 1 minus 0.36 over 100 equals 0.048. Then we're looking at 2 standard deviations. We can kind of cross this out to standard errors now. So we're looking for 2 of them. So we just want to multiply this by 2 to get 0.096, which is now we're going to call our margin of error. Okay. So we have P hat and we have the standard error, which we're now just going to call margin of error because simplify this. And so how can we kind of find this interval? So we just use P hat plus or minus margin of error, because we're 95% that it's within plus or minus 2 standard errors. So it's just going to be 0.36 plus or minus 0.096 equals, the lower bound is 0.264. The upper bound is, I believe, 0.456. Now we can just make this whole new statement, which we can say we are 95% confident. Again, using this confidence level right here that we started before, that P, and then we want to use P in context. So P, the true proportion of blue M&Ms is between, and then you just have our lower bound, 0.264, and 0.456. And now we have our confidence interval. Yeah, so thanks for tuning in.